Hello, it's Keith here, and this is lesson 1 of the advanced series of my 6502 assembly tutorials. Now, the advanced series is slightly different to the basic series. In this series, we're covering more things that are fundamental to the processor, but aren't things you will necessarily need on a day-to-day basis and may be more specialist. In this case, we're going to be looking at the extra commands on the 65C02, the later versions of the 6502 processor, and also the 6280, which is the PC Engine processor. The reason we're doing this at this time is some of those 6280 commands are actually essential to operating the PC Engine's graphics system. So we really need to look at these extra commands, but I thought it was a good idea to combine all of these together. So we're going to look at the extra 65C02 commands, which are available on the Apple II and the Atari Lynx of the Super Nintendo, and also these extra 6280 commands on the PC Engine. The PC Engine also has all of the 65C02 commands. Now, one important thing to point out is there is a later processor, the 65816, which is the 16-bit version of the 6502 that is contained within the Super Nintendo. We are going to look at that later, but that's going to be much more complex, and that's actually going to be an entire programming series on learning the 65816, and that's planned for next year. Now, when it comes to the 65C02, we have a few extra commands, but when it comes to the 6280, we have a lot of extra commands. We're going to look at them in the same way as we did with the original 6502. We're going to look at examples and see each of the commands in action. Now, if you're looking to program with the 65C02 and the 6280 commands, I'd suggest you get my cheat sheet. You can see the basic commands for the 6502 in black, 65C02 commands are in green, and the 6280 commands are in red here, so you can see all of the different options depending on the processor level you're looking to program for. Now, in general, with these tutorials, we're looking to program in a way that will work on all of the systems, so I tend to limit myself to these black commands, but if you are looking to only program for the Atari Lynx or the Apple II, then you're welcome to use these green commands, and if you're looking to program for the PC Engine, these red commands are available to you, and you do need to use some of those commands to be able to program the 6280's graphics hardware, as I've already said, and we're going to look at that in a later lesson. So what does the 65C02 offer to us? Well, essentially we have a few extra commands, so let's have a look at those now. So what are the new commands? Well, primarily we now have increment and decrement commands that will apply straight to the accumulator, so we no longer have to do add Cs to increase and decrease the accumulator, which is very nice indeed. We have the ability to push and pull X and Y directly without using other commands as well, which again is very nice. Another thing we have is the ability to clear a 0-page address. We have this STZ command, which will store a 0. And finally, we have a new branch command, which is a relative jump which will always occur. So this allows us, if we're doing code that we'll relocate in memory, to jump relatively to the current address, and that code will continue to work even if it ends up being executed in a different position. Another thing we have is the ability to use indirect addresses with a full 16-bit address, and you can see these here. I did briefly mention this before in the previous tutorials, but we're going to have a look at all of these new commands now today. So here's our example code. Let's execute it and see what happens. So we're going to be running on the Apple II because that is a 65C02 based system. So you can see here at the start we've loaded X with 1, Y with 2, and we've loaded the accumulator with 0 here, and we've shown our monitor to the screen. So that's what you can see here. We've then done a decrement and 2 increments of the A register here, just to show all 2 commands here. And so you can see that A is now 1 as a result of those calculations. We've then pushed X and Y and pulled them back, which has had the effect of swapping X and Y over. And that's where we are at this point. We've just called this monitor here to show this second line here. Now we've done a branch. We've just jumped one line here. It's just a test to show the command is actually compiling okay. And then we are dumping some memory from the 0 page here. So you can see this is the contents of the 0 page. Then we're doing a store of a 0 here. And we are clearing this 0 page entry here. And we're just showing the contents of the memory again here. So you can see that these commands all allow us to do various things to register a little bit more quickly. As I've said before, it's perfectly possible that if you want to compile code on 6502 and 65C02, you can substitute these commands with other commands that are just a little bit slower, and one option that is available to you is to create macros to emulate these commands so that you can compile fast efficient code on the 65C02 machines and similar slower code on the 6502 machines if that's what you want to do. Now, I don't tend to do that, and the reason for that is that systems like the Atari Lynx and the Super Nintendo, their processors are so massively fast anyway compared to a system like the Commodore 64 that optimizing the code just doesn't really make sense. It's the slowest machines with only the 6502 that need the optimization, not the 65C02 machines. So I don't use these commands in my day-to-day code. So those are the new commands that are available to us. As I've already said, there are some new options with regards to existing commands and existing addressing modes that are now available to us. And if you want to have a look at those, you're welcome to do so. We've already covered those addressing modes in my previous tutorials, so please have a look at those if you just need to refresh yourself. And just bear in mind that now those addressing modes are available to different commands. So that's pretty much all that we have on the 65C02. It's just a few extra commands there that may help us out and make our code a little bit more efficient. When it comes to the 6280, there's a lot of extra commands added. Some of these are very hardware specific, others are just nice commands that make things more efficient. Now at this point we need to actually start to discuss how the memory works on the PC Engine, because it's a little bit odd. I've probably mentioned in the past on the PC Engine that the 0 page and the stack don't actually occur at the usual 00XX range for the 0 page and the 01XX range for the stack. They actually occur at hexadecimal 2000 and 2100. Why is this? Well, it's to do with the way that the hardware is by default configured. By default, the PC Engine has its I/O registers in the 0 to 1 FFF range, and so because of that, the memory is expected to be at 2000 to 3 FFF. Now, the way the PC Engine works is that the CPU is going through a memory management unit known as the MPR, and all of the commands are being processed by that before they actually get to ROM, RAM, and hardware I/O. So we are able to configure that MPR to change the banks of our system to point to different parts of the physical hardware. Now the MPR works in 8 kilobyte chunks, so the addressable range is split from hexadecimal quadruple 0 to 1 FFF, hexadecimal 2000 to 3 FFF, and so on until E000 to FFFF, and these are each given a number from 0 to 7. So when we want to access a piece of hardware or a piece of RAM or ROM within a certain range, we can control the MPR and tell it to page that memory in. For example, when we start up, we will want to page in our I/O registers into MPR 0, so we can get to them from 0000 to 1 FFF. We need to page in our RAM from 2000 to 3 FFF, at least so we can use our stack if nothing else. And then we want to page in our ROM cartridge at the high area of the range. This is how the system is expected, but of course this range in between, we may want to page in the ROM cartridge in those as well, or for some reason we may want to have the RAM appearing in 2 places. Now there is only 8 kilobytes of RAM, so we wouldn't gain extra RAM by paging it in here, but we could do that if we wished, if it was more compatible with the way we wanted to program our system. So how do we actually control these? Well, there's a special command that will transfer the accumulator to the MPR, memory management unit. This will set one or more of the MPRs to the selected command, and that value in the accumulator will be the bank that we want to page into those MPRs. I said plural MPRs because depending on the bit mask, multiple MPRs can be set. For example, if we want to page in the RAM, that's bank F8, then we will select a bit, and so if we select bit 1 as 1, then we will page in the bank F8 into MPR1. However, if we set bits 0 and 1 both to 1, i.e. if we did TAM3, then what we would do is we would set both MPR0 and MPR1 at the same time to that new bank. Now, in all honesty, I don't think there's going to be many cases you're going to want to do that, and in my early days it was actually confusing me because I didn't realise that this was a bit mask and that it was causing me all kinds of trouble. But that's the way it works, and so if you want to set just a single one, you would use tam-1 for bank 0, tam-2 for bank 1, tam-4 for bank 2, and tam-128 for bank 7. So you could either use a bit format here or a decimal format as I've shown here. Now, the main ones we're going to want to use is we're going to use bank FF, which is I/O, F8, which is RAM, and 00, which is card ROM. And card ROM would expand to use more banks if the cartridge was bigger. So that's the basics of how we need to get started. Now, we've got the tam command to transfer the accumulator to the MPR, but if we want to get back the current state of the MPR, we can use the TMA command. So let's see those in action now. So let's look at our example of how we can use the tam and TMA commands. So here's the result of this code, and what's this code done? Well, first of all, we've loaded the accumulator with hexadecimal 33, and then we've stored this to 2000 and 2001. Now, if you remember, 2000 range is our RAM, so we've basically just stored these into RAM. Now what we've done is we've loaded the accumulator with 0, and we've used the tam command with bit 2 set. Now bit 2 is setting MPR2, and if you remember, bank 0 is the ROM of our cartridge. So we've effectively paged in the code that we're running into the 4000 to 5FFF range here. And then we've dumped that to the screen. And so you can see that here, that this random data here is the contents of our code. Now what we've done is we've loaded the accumulator with F8 and we've paged that into the same bank. And then we've done another memory dump, and we can see this has definitely worked, because although here we were seeing our cartridge ROM, now we're seeing that RAM that we marked with those two 333s here. So we've definitely managed to successfully page into that bank. We've used the TAM command here to read in from MPR2, but now we're using the TMA command to move from the memory bank and back into the accumulator. So we've effectively polled the memory hardware to see what bank is paged in, and we can see it's for F8 here. So we can see that has worked correctly. And that's how we can page in ROM and RAM and I/O registers into our system. And you can see here at the start of our code, we are paging in the I/O and the RAM here. We're not paging in the cartridge ROM because of course we're running from cartridge ROM, so that has already been paged in. We don't need to worry about that, but we do need to make sure our RAM and our I/O are paged in before we try to start using the system. So that's how we can page in hardware and also RAM into the system. Now, as I've said, we are paging in the I/O registers into the 0 range, and that's quite important when it comes to doing graphics. Now, within that range, all of the registers repeat over and over again. So we can write to quadruple 0 or 0100 or 0200, and we'll write to the same addresses. And this is quite important when it comes to using our assembler, because our assemblers will tend to get confused when we are writing to an address where the top two nibbles are 0. It will think we're writing to the 0 page, and of course in the case of the PC Engine, the 0 page doesn't exist at that memory location. What this effectively means is when we want to use those registers, within VASM at least, we want to write to 01 and then our register number. But we don't really need to worry about that at this stage. I just thought I'd explain it at this point. The important thing you do need to know is that there are 3 very important registers within that memory range that relate to controlling the hardware of the video system. The first one is where the bottom byte is 0. This is the ST0 register, and it selects one of the video registers. The second one is at 02. This sends the low value of a word to the video hardware, and 03, which is also known as ST2, will set the high byte. So we have 3 addresses, 0, 2 and 3, and these have alternate commands, ST0, ST1 and ST2. You see, when we want to select the register and write data to that register, we have 2 options. We either address the memory directly, or we use the ST0, ST1 and ST2 commands to send a byte directly to those ports. Now, the ST0, ST1 and ST2 commands only exist on the 6280 processor, of course, and because they are a single byte command and then a single byte of data, it's faster than loading into the accumulator and then sending to memory addresses, but of course it is more limited. Now, what do we need these for? Well, essentially everything for graphics. If we want to send data to the hardware to set up our tiles, we need to use these memory addresses or these ST commands. If we want to actually draw those tiles to the screen, in other words draw text to the screen, we need to select the memory addresses and then write byte data to the tile map, and we're going to do that now. So you can see here we're going to be using some of the registers, and the ones we're going to be most interested in is video register 0, which is address select. This allows us to select a memory address within the video memory that we're going to write to, and then register 2, which is the data write register. Once we've selected this, the bytes we send to the L and the H port will actually be written to that address in memory. So that's what we're going to do now. What we're going to do is we're going to select byte 0 of the video memory, which is the top left of the visible tile map. We're then going to write some bytes into it. We're going to set the low and high bytes to 1. The high byte of 1 means we're skipping the first 256 tiles, and then the second byte of 1 means we're showing tile pattern 1 within the tile map definitions. Now, the reason we skip 256 tiles is because actually the first few tiles are actually overlapping the memory of the tile map, so they're not usable within the system. But anyway, all you need to worry about at this point is we're writing data to the tile map, and we will immediately see that visible on the screen. So just to reiterate, ST0 is selecting a register. We're selecting register 0, which is address select. ST1 is writing to the low byte within that register, and we're writing a 0. ST2 is writing the high byte of that register, and we're writing a 0. So we're selecting address 0. Then we're using ST0 to select register 2. ST1 to write the low byte, which is going to be a 1, ST2, which is going to be writing the high byte, which is also a 1. Now, whenever we write data using ST1 and ST2, the memory address will auto increment. So we can then write another byte. So we're writing the following character within the tile map here, just to the neighboring tile on the screen. And then we're selecting a new line, and we're moving across 32 tiles within the tile map, which effectively moves us down a line. We're then defining another tile here, again selecting the data write register and writing some data here, but then we're going to do something slightly different. What we're going to do is we're going to map in the IO registers using that tam command here, and we're going to again map it into that 4000 range. And then what we're going to do is we're going to do effectively the same thing, but this time we're going to directly address the hardware registers via memory. Now, if you remember, each of these ST0, ST1 and ST2 commands can be accessed from memory at the addresses 00, 02 and 03. Now, why these aren't called ST2 and ST3, I don't know, but they aren't, so that's what they are. And you can see here we're effectively doing the same thing. We're now selecting memory address 64, and then we are selecting the data write register again, and we're writing some new bytes to it here. So let's see that in action now. So what have we done? Well, relatively little actually, I suppose, but what we've done is we've selected the top corner of the screen and we've printed an exclamation mark. The memory address is when we write auto increment, so when we write our second one here, we've written a quote here. Then we've moved down a line here by adding 32 to our memory address, and we've set this hash symbol here. And finally, when we've done our memory addressing directly here using the tam command here, we've written this dollar symbol here. See, the point I'm trying to make is by altering the video memory, we can effectively immediately alter the content of the screen, and we can do this either with the ST0, ST1 and ST2 commands, or by directly addressing the memory in whatever bank we have the IO registers paged in. So that's the point I wanted to make there. And those are the only two ways that we can alter the video memory. So we either need to use those efficient ST0, ST1 and ST2 commands, or directly address the memory, which works fine, it just takes a few extra bytes, so it may not be appropriate in all cases. Now ST0, ST1 and ST2 can only work from fixed values, they can't work from the 0 page or anything, and so in those cases we are going to have to write to memory addresses using the second method there. So that was a little bit complex, but it was the most important part of the options we're going to be looking at today, because these are the ones that we can't really do without when it comes to actually graphics programming. Now we're going to look at some much simpler stuff. We've got some swap commands for our registers, so let's have a look at them. So very simple here. What we've done is we've loaded the accumulator with 1, X with 2 and Y with 3, and then we've swapped X and Y, which you can just see here. X and Y have swapped over. And then we've swapped A and X here, so you can see A and X have now swapped over. And then we've swapped A and Y, and so you can see A and Y have swapped over. And then we've cleared X and Y here. So we've got some commands that allow us to quickly set and clear registers just to save extra stages, pushes and pops and things like that. So these are great options if you want to quickly shift your registers around. So there we go. Now the 6280 processor by default runs at 7.16 MHz, which is very fast for an 8-bit processor. The vast majority of systems around that time were 1 to 2 MHz, and that's part of the reason that the PC Engine is often mistaken for a 16-bit machine when it's actually technically 8-bit. That and the graphics hardware were relatively advanced for the day. Now, as I say, by default it runs at 7.16, but we can actually slow it down if we want to 1.78 MHz. I think the main reason to do this would probably be for the handheld systems. There was a handheld PC Engine released later, and so I guess you would probably want to do that if you could to save power on that system. But generally speaking, there's not really any reason we're going to want to do this unless our game is running far, far too fast and we think this is the simplest way of slowing it down. Anyway, we have two commands to do this. We have a CSL for low speed mode and a CSH for high speed mode. So what we're going to do now is we're going to do a little test where we're just going to print some characters to the screen with an artificial delay in and just see the difference in the speed depending on those modes. So here's the low speed mode. You can see the A's are filling slowly. And then when this gets halfway across the screen, now that's the same code running again in the high speed mode. So you can see there's a huge difference in the speed there, and we can switch speeds whenever we want with CSL and CSH. Just very straightforward there. Now my code in these examples is always running in high speed mode, so I'd really suggest, unless you have a good reason to slow it down, I'd just use the high speed mode. Now we're going to look at a very interesting command, which is the T flag. Now there is a special flag on the 6280 which is just called the T flag, and we have a command called set which sets that T flag. What the T flag does is it alters the functionality of some of the commands relating to the accumulator, ADC and E or A and SBC. What it does is it changes these commands so that rather than affecting the accumulator is actually untouched, and the equivalent effect will be applied to an entry in the 0 page defined by the X register. Now that's quite strange, I know, but effectively if we set X to 1 and then we do the ADC command, 0 page entry 1 will be changed and the accumulator will be unchanged. Whenever we use the set command, the next command that uses the T flag will reset the T flag, so any following commands that use the accumulator will work completely normally. Effectively, we've got an option to switch the next command to apply to a 0 page entry rather than to the accumulator, but it does only work on a few commands. So let's try this little example here and see it in action. So what we've done is we've loaded an entry into the 0 page here, hexadecimal 60, and we've shown it to screen. Then we've loaded X and A with 0. Now what we've done is we've cleared the carry, we've turned on the T flag, and what we've done is we've done an add with carry which should apply to the accumulator, but because it follows that set command with the T flag set, it does not apply to the accumulator, it actually applies to the 0 page. What we've done next is we've done another add with carry, this time of 2, and because the T flag is reset whenever a command uses it, the next command is actually applied to the accumulator, and you can see that here because the accumulator has now been changed to 2, and the 0 page entry which X points to, this 0 here, is now 61. Now of course if we change the X register and then set the T flag again, we will apply to a different 0 page entry, and we've done that here. We've incremented X, so X is now 1, set the T flag again because remember it will have been cleared by this command, and then we've done add with carry of 3. And you can see that has been loaded in to memory address 1 within the 0 page here. Of course, because the 0 page isn't at 0 on the PC Engine, it's at hexadecimal 2000. So that's how we can use the T flag, and it effectively allows us to protect the accumulator and use the 0 page instead. And this may be useful if you need your accumulator for other things, or this may be useful if you're in a loop and you're doing the same mathematical change to a wide variety of entries within the 0 page using X as a counter. Anyway, quite a curious command there and an interesting addition to the 6280 processor. Now we're going to look at some very powerful commands. On the PC Engine we have some commands similar to the Z80 LDIR command. These are TII, TDD, TIN and TIA. These are allowing us to copy bulk data from a source and a destination, and these are designed for fast copying of data, I think for the video memory primarily. Let's have a look at them and see what they do. Okay, so first of all we've dumped our memory here, and then we've got our TII command. Now the format of the command is source, destination, byte count. So it takes 3 parameters, which is very unusual for the 6502, and I really have to thank the author of VASM who actually added the support for these commands to the VASM assembler for me, because because they weren't supported originally, but he was very kind to actually extend VASM to support this PC Engine's processor. So we are now able to use these commands within VASM. So we've got the source, which is some data, which you can see down here, these bytes here. We've got the destination, which is our 0 page memory, hexadecimal 2000, and our byte count is 8 here. And so the results you can see here, and we've copied them here. Now it's important to understand that TII starts from the left hand side and goes to the right hand side, but in this case of course we don't really see the direction the copy occurred, we just see the result. We also have a TDD command which works the opposite way round. We've got our destination here, we've got our source here, but we're starting from the end of the range this time, and our destination here, but again we're starting from the end of the range, and we have a byte count here. So in this case we're writing the other way, and we're going to be using this clearing data here just to set everything back mostly to zeros here. But you can see even though we've started from the end to the start this time, the actual result is in the same order because both counters are going down at the same time. It's not reversed the range or anything. Now unfortunately all of these commands don't allow you to work from 0-page entries or from registers, so they're always fixed ranges. But I guess if this was a concern for you, you could always use self-modifying code and actually modify in the ranges that you needed. But I think these are mainly for copying bulk data from the ROM to the RAM or from ROM to the video memory. So I think that's why they're using fixed ranges like this. Now, those are the two most logical ones, but we do have some slightly odd commands. We have the tin command. What the tin command does is it copies a source range, but it copies all of that range to a single byte destination. Very strange, really. So you can see here we've copied our entire range again. We've copied some data and we've copied the 8 bytes in entirety, but when we view the range you can only see the last byte because they've all been written to the same destination. Well, I think this is relating to those I/O registers within the hexadecimal quadruple zero range. I think this is designed to allow you to stream data to maybe the sound chip or maybe the video chip, and in that case you might want to stream a large amount of data to just a single destination address, and that's what I believe these are for. Then it's not a command I've ever used, but that's what I think it's designed for. We have an even odder command, which is TIA, which is transfer increment alternate. What this does is it alternates between two destination addresses. So we've got our source data, our byte count, and our destination, which is hexadecimal 2000. But it will actually write to hexadecimal 2000 and 2001, and it will alternate between the two. And we can see that here because we've got the last 2 bytes now visible, and you can assume that 1, 1 and 2, 2 will have been written here and here. 3, 3 and 4, 4 will have been written here and here, and so on until we've completed our byte range. And well, what's this for? Well, I think it's pretty obvious that this is designed for writing data to our video memory, because if you remember, our video memory uses a pair of memory addresses within the I/O range here. And so if we wanted to write a sequence of bytes into, for example, the pattern data or into the tile map itself, we could do that here. So if we had a cache of data that was a buffer we were building up, or if we had some sprite definitions we needed to load into memory at the start of a level, we could use this to stream that data straight into memory quickly. But they're very odd commands, and again, you don't need to use them. With regards to the fonts within my examples here, I was actually converting the fonts from 1 bit per pixel to 4 bits per pixel, so it wasn't possible to use these commands because I needed to actually do mathematical operations on the byte data first. So clever and powerful commands, but may not be useful depending on what you're using them for. Now finally, we have a rather elaborate set of bit level operations. These will all apply bit operations to various addresses within the 0 page. We've got RMB, which will reset a bit, SMB, which will set a bit, TSB, which will test and set a bit via the accumulator, TRB, which will test and clear a bit, and TST, which will just test an address. Now, in addition, we also have some branching commands. BBS will branch if the bit is set, in other words, if it's 1, and BBR will branch if a bit is reset, in other words, if it's 0. So let's try all of these out. Okay, so what have we done here? Well, what we've done is we've shown the 0 page range, which is currently in hexadecimal 2000, and then what we've done is we've done some set commands to various bytes within that range. So we've set byte 1 within the 0 page range, and we've set bit 0 of that. So you can see that this is now changed to 1. We've set bit 1 of address 2, so you can see that's 2. And then we've set bits 2 and 3 of address 3, so you can see that's now changed to a C. We've then done reset commands to 3 of those addresses, so you can see these 2 have changed to 0, and this one's now cleared down to 8. So we can change 0 page entries here without using the accumulator in any way. Now we're using this show bit command, which is using the branch if bit set command here. And we're also using the branch if bit reset command here, and so we're testing bit 0 and we're showing a 0 if the bit is 0, and we're showing a 1 if the bit is 1 here, and we're just moving to a new line afterwards. So first we're running it with the default value of 0 here, so we are showing a 0, and then we are setting bit 0 of that memory address and running it again, so the second time it's showing a 1, and so you can see we are successfully able to test the bit 0 of memory address 0 using BBS, branch if bit set, and BBR, branch if bit reset here. Now, as well as directly operating on the bits like that, we can also use the accumulator. Now, if we load the accumulator with hexadecimal 80, which is bit 7 set, and then we do a test and set bit on hexadecimal 0, you can see we can actually set the top bit. And this has effectively set the address from the 1 that we had it at this point to hexadecimal 81 here. We can also do a reset in the same way, and it will set the bit back to 0 here. And it's important to understand that it's not just setting these, it's actually setting the 0 flag accordingly, ineffectively doing an AND of those two values. Finally, we have a test command, and we can use that here, as you can see. So here we're loading hexadecimal 80 in memory address 0, and then we're testing to see if bit 7 is set, which of course it is here, and then we're branching if bit 7 is not 0, which of course it isn't. So we're skipping a line here because bit 7 is not 0. Then we're testing bit 1, which of course is 0, and this time the branch will not occur, so we're showing a 0 here, which you can see just here. And then the final result of the memory address is shown here, so you can see bit 7 will set there. So we've got a wide variety of bit operation commands here. Now, these aren't something I've tended to use. Now, these aren't something I'm going to be using in my tutorials because, as with most of the stuff, I'm trying to stick to the basic 6502 commands. Two reasons for this. Firstly, I want my code to work on as many systems as possible. But secondly, it gets very confusing if you come to rely on commands that don't exist on some systems and do exist on others. So while occasionally I will use these platform-specific commands within the code for example, my graphics routines on the PC Engine, you're never going to see them within the general code because it would mean that the code wouldn't work on most of the systems. Anyway, I hope you found some of these enjoyable and interesting. If you can think of any recommendations on times that I should be using these commands, the specialist ones, please let me know. As I said before, if you're interested in the 65816 processor, we are going to be looking at that at a later date, but it's very complex and it has a lot of extra commands and functions, so it's not something we're going to be able to look at the moment. Anyway, thanks for watching today, and goodbye.